Okay, so let's talk about reactions, and let's talk about different types of reactions. Now, one reaction we can talk about is equilibrium, and equilibrium is a reaction in which there is a forward reaction and a reverse reaction. So we go from the reactant to the products, then you also have a reverse reaction, which, if we were to actually draw it out correctly, not like this, but your products are now the reactants, and you get a reverse reaction. Now, equilibrium, and I think a famous example of a reaction which is in equilibrium is the Haber process. So the Haber process is the process of producing ammonia from nitrogen and hydrogen. And this reaction has a forward component and a reverse component. So ammonia can break back down to nitrogen and hydrogen. And one thing that we kind of wonder is, well, why is it then that this reaction is occurring in equilibrium? And so, essentially, we're going to be talking about something known as Le Chatelier's principle, which is going to explain how a reaction and how we can predict which one, the forward reaction or the reverse reaction, is going to occur at the greater rate. So when the system's in equilibrium, the rate of the forward equals the rate of reverse. But when the reaction conditions change, there is actually a shift in the rate of the forward or reverse reaction to restore the equilibrium we just talked about. So, let's begin our discussion by talking about a pretty important concept before we get into Le Chatelier's principle, which is known as the equilibrium constant. Now, what the equilibrium constant is it's the expression which we can use to find the concentration of species which are in equilibrium. And so the equilibrium constant is known as KEQ, and it's defined as the concentration of the products raised to their stoichiometric power all over the concentration of the reactants raised to their stoichiometric powers. So as you can see, we have 2 moles of ammonia, so we put a 2 there. We have 3 moles of hydrogen, so we put a 3 there. So this is the equilibrium constant. So, let's talk about how we can find the equilibrium constant for a specific reaction. So let's take this reaction, for example. So in this reaction, what we have is HI going to H2 plus I2, so it's decomposing. Now, can you write the equilibrium constant for this reaction based on the example we just did? Pause the video and have a go. So it's products over reactants, and each product has a coefficient of 1. The reactant has a coefficient of 2, so this would be our equilibrium constant. Now, how do we calculate the equilibrium constant? Well, first of all, we need to know what the concentrations are at equilibrium. Remember, this is at equilibrium. So, if we said, for example, that the concentration of H2 was 0.12 molar, the concentration of I2 was 0.25 molar, and the concentration of HI was 0.25 molar. What we'd get is our equilibrium constant, so we'll just cancel these. It would be 0.12. So that's just an example of how we would calculate the equilibrium constant. Let's have a go at another example. Okay, so this time we will say that the KEQ is 0.23. What is the equilibrium concentration of HI? So we are trying to figure this out. If we know that H2 is 0.075 molar and I2 is 0.32 molar. So we've been given the equilibrium constant and we have one unknown. So let's write the expression for the equilibrium constant. And we want to find this. So let's rearrange it. So HI squared is equal to H2 I2 all over KEQ. So if we have a square, we need to take everything to the power of 1/2 to find the concentration. So the concentration of HI will be equal to this. And when you plug that in, you should get 0.32 molar. So we've talked about the equilibrium constant and how to calculate it. And let's just talk about certain things that actually won't be included in the equilibrium constant. So equilibrium constants are concentration dependent. I'll explain why this is important. Certain cases are apparent when we don't have a concentration for something. For example, let's have a look at this equilibrium. Let's take PbSO4 goes to Pb2 plus SO4 2 minus. Okay. Now this is a solid, lead sulfate. These are aqueous. Solids cannot be compressed, and their concentrations cannot be changed. So we don't include solids in the equilibrium constant. The other thing we don't include is pure liquids. So if we take, for example, H2O plus HCl goes to H3O plus Cl minus. We do not include water in this equilibrium constant because it is a pure liquid. So let's have a go at writing equilibrium constants for some of these reactions. Okay, KEQ. Let's start with the first one. So we got NH3 squared, N2, and H2 cubed. Let's try the next one. So you see, in this case, what have we encountered? We've encountered a pure liquid, which is water. But what if I change this to a gas? Would it be included? What do you think? Well, the answer is yes, because you can compress a gas. So because we have H2O as a gas this time, it will get included in the equilibrium constant. So that is kind of a very key component of this whole process, is that you have to be aware of these happening. Sorry, I've made a small mistake. That is not supposed to say SO2, that is supposed to say O2. Sorry for the confusion. So, this should say O2. Okay. Let's move on to another example. What about this one? Silicon solid plus O2 gas goes to SiO2, and that's a solid. Write the equilibrium constant. So we have the following. Our products are a solid, so we don't include it. So we don't need any products actually this time. And one of our reactants is a solid. So the equilibrium constant is actually just 1 over O2. Seems fairly straightforward so far. So this is how we find the equilibrium constant. Now, the next thing is how do we know what is favored in an equilibrium reaction based on the equilibrium constant? Okay, let's take this example. Okay, what do you think is favored if I told you that the equilibrium constant was 6.3 times 10 to the minus 11? Pause the video and tell me if the forward reaction is favored or the reverse reaction. So let's have a look. The equilibrium constant is defined as the concentration of products over reactants. And the products are raised to their stoichiometric power. We can call that A, and then we can call that B. If there's more than one product and more than one reactant, you'd have, A, B, C, and D. In this case, what we've seen is that this equilibrium constant is pretty small. So that indicates that there is a high concentration of reactants, because that high concentration of reactants will lower the equilibrium constant. If the denominator is big, then the top of the fraction will be decreased, or the value of the fraction will be decreased. So we can say that the reverse reaction is favored. Second one, let's have a look at this. Okay, so in this case, let's have a look. We have the following, and this is a gas, this is a gas, this is a gas, and this is a gas. And the equilibrium constant is 5 times 10 to the 3. So, what's favored, reactants or products? Look how big the equilibrium constant is. It's much greater than 1. And I'll explain why that's important. What does that mean? It means that the products are favored. So I think you can kind of get the gist of this now. If the equilibrium constant is products over reactants, when it is equal to 1, that means that both are favored. The forward reaction and the reverse reaction. If it's less than 1, so KEQ is less than 1, it means that the reverse is favored. And if it's much larger than 1, if it's larger than 1 rather, the forward is favored. So, the next thing to kind of consider as well, what do you think affects the equilibrium constant? So the equilibrium constant is a temperature dependent. It is not concentration dependent. The equilibrium constant does not change with concentration. The equilibrium constant will change with temperature. So, essentially, let's kind of think about that. So, what do you think happens to the value of KEQ when the forward reaction is endothermic And what do you think happens to the value of KEQ when the forward reaction is exothermic? And in both cases, we increase the temperature. Pause the video and see if you can figure it out. So KEQ goes up when the temperature of an endothermic reaction increases. And the reason is because increases in temperature favor endothermic reactions. KEQ goes down when the temperature of an exothermic forward reaction increases. So, KEQ increases when we increase the temperature of an endothermic reaction, and KEQ decreases when we increase the temperature of an exothermic forward reaction. That's pretty much it. And so, to summarize in this video, we talked about how to find the equilibrium constant, how to calculate it, and how to use it to find an unknown. We also talked about the fact that we don't include solids and pure liquids in the equilibrium constant, but we include gases. Anything that can have its concentration changed, we include. Then we also talked about which reaction is favored when we have a equilibrium reaction and we are given the equilibrium constant.